Hello everyone, I am Yao He from the Chinese University of Hong Kong, Shenzhen. And this summer, I collaborate with Dr. Yu and Dr. Sebastian Scherer from Carnegie Mellon University, working on GPU-enhanced front-end for visual-inertial odometry. State estimation is one of the most fundamental modules in a lot of applications, such as autonomous driving and robotics navigation. The state-of-the-art approaches are the visual-inertial odometry algorithms, which combine cameras and inertial measurement unit to solve the odometry problem very accurately. Even though these algorithms can solve the problem accurately, the CPU usage and computational latency are a significant problem. Jing tests different VIO algorithms on different NVIDIA hardware. And from the figures shown here, we can see that most of the VIO algorithms has CPU usage about 150%. This is essential, especially on some computational resource-limited hardware. In recent years, a lot of work have been utilized the GPU to enhance algorithms in the field of VIO. Noticeable approach are the NVIDIA Visual Programming Interface, in abbreviation VPI, and CUDA Visual Library VILIB. In our work, we aim to reduce the cost on CPU usage and computation latency using GPU-enhanced module while maintaining the accuracy. Our focus is on the front end, especially the feature detection and tracking module, because the front end processes a large volume of data and the processing can be solved in a parallel way. We select this model as our baseline to build a new front end. We substitute the module that consumes essential amount of CPU and computational time with corresponding module in VPI and VILIB. And we also test the new VIO on public datasets. In terms of VPI, we directly substitute the feature detector and tracker in this model with equivalent module with VPI. And we modify the underlying data structure to reduce cost on transportation data between GPU and CPU. When the camera image comes in, it will pass to the VPI pyramidal allocate optical flow to track data from the last frame, and the image will also pass to the VPI Harris corner detector to detect new points. The newly detected point will go to a filter implemented using the core tree algorithm to make the distribution as uniform as possible. This is the entire pipeline of the front end using the VPI. The idea of the core tree algorithm is very simple. In each iteration, you will split the image to 4 sub-image nodes until the number of image nodes is greater than the number of needed feature points. And it will select the best feature points in each image node. From the figure shown on the right, we see that after the quad tree, the distribution of the feature points becomes more uniform. If the distribution of the point is not uniform enough, the initialization part of the VIS model is not robust. In terms of VILIB, we modify the tracker and detector in VILIB and encapsulate them into functions, having same input and output formats as equivalents in OpenCV. And then we substitute them in this model with new module in VILIB. However, during our experiment, we noticed that the VILIB tracker fails to do correct tracking because the tracked feature points have serial drifting. So we kept the old CPU version feature tracker. We also propose our own RANSAC algorithm on GPU. However, the performance does not satisfy our expectation. So I omit some detail here. If you're interested, you can come back to see it. I can show the reason why the performance does not satisfy our expectation. Since the size of feature point collected in this model is limited to a relatively small amount, copying data between CPU and GPU becomes significant in the entire RANSAC process. Therefore, copying data and releasing memory consume a lot of time of RANSAC on GPU. This makes it slower than that on CPU. So we do not include RANSAC on GPU in the following test. This table shows the CPU usage, and computational latency of different versions of this model. From the table, we see that this model VPI has the most significant reduction on CPU usage and computation latency, achieving a reduction of 40.4% and 50.6% respectively. Modules from VILIB do reduce the computation latency, but they do not reduce the CPU usage. In terms of VILIB, we test the fast feature and high-res feature. And when fisheye cameras are used, which are shown on the last two columns, we notice that except this model with VPI, the other three versions all have a CPU usage close to 100%. And we also test the VIO on public data sets. The two figures on the left show the rotation RMSE and translation RMSE on Euro dataset. We see that this model with VPI has similar accuracy as that of this model, and sometimes it is better, even better than this model. On the other hand, this model with VILIB loses accuracy to some extent, especially when testing the V102 dataset and V202 dataset. And the figure on the right shows the estimated trajectory on V102 medium dataset. From the figure, we can see that except VILIB, this model, VILIB fast, the other three types of this model have good estimation results. This model VILIB fast has serious drifting compared to the other three versions. So in conclusion, the VPI enhanced this model both maintains the accuracy of the VIO and reduced the CPU usage and computational latency significantly. It reduced the usage and computational latency by 40.4% and 50.6% respectively. VILIB reduces the computational latency to some extent, but it does not reduce the CPU usage. It also has large estimation errors compared to other versions of this model. Therefore, we choose VPI to enhance the performance of the VIO and use it to build a new front end. That's all. Thanks for your attention.